So I'm going to give a bit of a talk, a bit of a change up from what we just talked about, and focus more on data science with Python. In particular, how we can use image and text in our data science pipelines, in our model building. So just briefly, I'm Joshua Loyal. I work at a company called DataRobot. We do predictive analytics. That's my email if you want to reach me later. And also, the repository for this talk is available on my GitHub repo, which you could find there. So what we're going to do is we're going to walk through kind of a basic data science problem that involves both images and text. In particular, we're going to think of kind of an example, kind of like an Amazon, where we have a bunch of products in our library, and we want to be able to sell them to users. So in particular, we have stuff like watches and their descriptions, and we want to be able to create an algorithm that automatically tags them, maybe because we want to do better in our inventory, or maybe we want to be able to tag things to better sell things to people. So that's kind of like the business problem. But if we're going to do data science, we have to kind of frame it in a way that kind of works for model building. So in particular, you could kind of have a model like this, where we have both an image of a watch, for example, and a textual description. In this case, it's something like a Swiss Army women's collection black silver dial, for example. And what we want to do is build a model that either classified either as clothing or an accessory. So it's just a binary classification problem. Even that is still like a little too high level for something like a model to build. So the most basic, one-line example of what we're going to do is we're going to basically come up with a way to give a probability to a product at either clothing or an accessory using what we have, which is the images and the text available. So just quickly, the data we're going to kind of process in this talk comes from this particular paper from Julian McCulley, who's a researcher at the University of San Diego who did a lot of research on Amazon data and how to build data pipelines. So we took a data from that. Just in your head, what we have is a CSV file, which is going to have our images and text inside of it, and then a separate directory with the images kind of in JPEGs sitting in that same directory. So in Python, the main library to use for data analysis is Pandas, which is kind of what we're going to start out with. It allows us to load up data into these things called data frames, which are columnar data sets. So you'll have rows, samples in one part, and then the columns in the other. And so we can kind of take a look at what we're looking at here. We have a title, which is the text we're going to deal with, and then we have a bunch of image files, which are the location on disk, and in this case, which is a bunch of JPEGs. And then we have the product category, which is what we're trying to predict. In this case, clothing or accessories. You can see there's kind of a mixture of things here. There's hats, there's beads, there's rings, and so it's kind of a diverse set of products that we need to start looking at here. So again, just to set the stage before we even get into modeling, it's very important that you kind of think of the pipeline beforehand, because you have to set that in stone. This is kind of a science. This isn't just playing around. So we need to be able to set this up, especially for reproducibility. So the idea here is you'll take a data set, you'll split it up into what we call training and testing. The training set is what we'll build our model on top of, and the testing set is kind of what we use to be able to tell, if our algorithms are working before we even deploy it to production for our customers to use. The next bit, which is kind of my favorite modeling cycle, is this transform, visualize, and model cycle, which comes from this R for Data Scientist by Hadley Wickham, which is kind of the idea here that we're going to make our features, but we're going to have to make sure that we have a way to visualize what we're doing, because it's very easy to make features, but then when you look at them, they don't make a lot of sense, and we know right away the model is just not going to work. So it's very important at any step of the phase to always visualize what you're doing, and then, of course, modeling. And so we'll have that pipeline, and then we'll also set up a way to validate it on the test set and to tune our models. So the first step you might ask is, how do we even split it up in the first place? And you should always just look at your target. Again, we just visualize right away. And here I'm using a library, again, called Seaborn, which is a library built on top of Matplotlib, which is a wonderful library for plotting. This is just a layer on top of it. Makes it very easy to make simple plots. In this case, we can see that this is the target distribution. This is just a bar plot. You can see the counts for each class of clothing and accessory. They're kind of roughly balanced. So we know we could kind of just get away with a simple 20-80 split. You might have to do something more complicated if it was more unbalanced. So just kind of briefly kind of walk through kind of what you would do in Python to do something like this. You would take our Pandas object and we'd use a library called scikit-learn, which has a wonderful thing for a variety of things, but in this case we're going to use the train test split function to split it up into that 20-80% splits we talked about. So again, we pop off the product category, which is our target, and then the X array, and then we pass it through the train test split with a 20%. And one thing just really to point here is always fix your random state when you're doing these kind of splitting, because it was kind of funny, when I first made this talk, I had to actually redo it like a few days ago. And the fact of the matter was that I had fixed everything beforehand, so we were always comparing apples to apples, oranges to oranges. You weren't having, one test split, come back later and have a completely another split, and it's just going to confuse everything. And this on that kind of same line, always save everything to disk. So this way, when we again build our models, the test set's always the same and everything's A-okay. Okay, so now just kind of gets into like kind of the main part of the talk, and that's how we even deal with images in Python, right? These aren't just like numeric values, they're not categorical values. They're very complicated objects that we want to be able to deal with in a systematic way. So just briefly, how is an image even represented for an algorithm to deal with? In this case, it looks like it's an array. So we have a picture here of a dog, right? We know what that looks like, but for a computer, you go in, it has an RGB value, as you probably know, red, green, blue. Each one of those is a single array. So we have a three-dimensional array. The first two dimensions are the width and height, where we are in the image. For example, are we on the nose, or are we on the top left corner or top right corner? And then the third dimension is the RGB values of the pixels, right? So a wonderful library for dealing with images is the Pill library, or in this case, it's the fork of a Pill library called Pillow, which you could easily use to load your images and manipulate them. All right, so it's as simple as loading pill.image. We look at the file, we just call open, and we convert it to an RGB pill image object. Right? The next thing you're going to have to do is obviously resize it to a constant shape. So a lot of our algorithms going downstream are going to expect all the images to be the same size. In this data set, for example, we had images that were like 128 by 250, 250 by 220. They were all over the place. So right here, we kind of resize it to the same size. I chose 224 by 224. The reason for that number will make sense a little bit later when we go into the model building. And this quickly, you can see there's a second argument. That's kind of the anti-aliasing argument. So what will happen when you resize the image, for example, when you blow it up, you'll add pixels to the image. We have to tell the algorithm what the color of those pixels should be, and that's kind of what that anti-alias is doing. And finally, to convert it into array, you just use numpy. You call as array on this pill image, and it converts it to that three-dimensional array we looked at in the previous slide. On the left part of this slide, you could see a visualization that I did, right? We're visualizing everything that we do, this conversion. We have to make sure that what we loaded, right, is actually the images we expect. And so code to make this is, again, available on the repo. But what it is kind of assorted in terms of the hue. So you can see it goes from darker colors to lighter colors of the objects. And you can see already that these images have some structure to them, right? For darker images, you see things like shoes, pants, hats. Basically, clothing is kind of darker colored already. And then when you go to the bottom, you can see like kind of lighter colors, right? Jewelry is kind of silver and more pastel. And so you can see there's some nice structure here right off the bat. So why are images hard, besides the fact that they're more structured than normal? Well, the problem is there's also a lot of variation. And these are stuff you're going to have to worry about when you look at your features and you train your algorithms, right? Stuff like if I move my head and I look this direction, or if I look straight at you guys, I'm still the same person, but the algorithm's not going to know that right off the bat. It might just think I'm someone completely different. Size variations as well, shorter and taller, it's still a person, but it's not apparently clear, and just a bunch of other things. And a bigger one is interclass variation, right? Like there's all these different types of chairs. In our case, there's going to be different types of bags and T-shirts, and coming up with an algorithm that knows all that stuff is very difficult, right? So we have to make sure whatever we do, accounts for all this. So one of the easiest ways to deal with this is take something that has seen all this variation and knows about this variation and just use that. Stand on top of the shoulders of giants, as I say. So we're going to talk a bit about transfer learning. And the idea behind that is taking these models, which have been trained on a data set called ImageNet, which is a data set that contains 10 million images of 1,000 different classes, of variations of different dogs, cats, bags, clothing. So it's kind of seen all these different things and should be able to tell the difference, between all this. And then we could train a simple model, right, in Python that will be able to classify these things very well. So this slide is a little complicated, but if you could take anything away, if you could take anything away from this talk, and if someone asks you what model to choose, this graph is going to help you a lot. So to walk you through what's happening here is we have on the x-axis what's called the operations. This is kind of the time it takes for this algorithm to process an image. The further you are on the x-axis, the longer it's going to take, which is going to be a while if you're worried about latency, right? On the y-axis, you have the accuracy. That's how well the model is going to perform. And then the size of one of these dots is how many parameters the model have. And that means that's going to affect the memory usage, right? So if the bigger the dot is, the more space it's going to take up on your GPU or your CPU. For example, a lot of people use VGG, which is that giant green dot there, and they just run out of memory immediately. The thing's huge. It takes up about 5 gigabytes of RAM alone. So the main takeaway here is you can kind of see this elbow-shaped curve as you go up here, right? And so we want to choose something that is relatively fast, is relatively accurate, and doesn't have a lot of parameters, has a small little dot. And the one that looks very good here is ResNet 50. It's kind of the pink dot up there. You can see it's relatively fast, it has high accuracy, and it's small in terms of memory usage. So we'll go ahead and use that. So moving on to neural network libraries in Python. A wonderful library is Keras. It has kind of a lot of the high-level stuff for you to use. In this case, it has ResNet 50, the model we want. It's contained in this applications folder. So you might ask, what is ResNet 50? Well, not to go into too much of the details, but it's made up of kind of these stacked modules, which I have on the right. It takes an input, it applies a bunch of neural network layers to it, convolutions, which are sliding windows looking over each feature patch, batch norm, which is a way to help the training of the algorithm, and then it does that twice. And essentially, it stacks this 50 times on top of each other, and that's where the number 50 comes from, 50 of these modules stacked on top of each other. So as far as what ResNet you should use, these are kind of the important parameters. You don't want to include the top layer. And the top layer of ResNet 50 is kind of the classification layer. That tells you, out of the 1,000 classes in ImageNet, what class was it. That's not important for our problem because we only want clothing and accessories, so you could kind of chop that guy off. The weights come from ImageNet, as we said. And then you could see why I chose 224 by 224. So ResNet expects a particular input shape of the image. That's 224 width, 224 height, and 3 RGB pixel values. So we had to resize everything in order to fit it into the model. So again, kind of just to go over a bit of the code real fast of how you would actually do this in Python. You would take our data frame with the image files, you convert that to a list. You'd set up a few parameters saying how many images do I want to pass through the network at a time, in this case 32. That's kind of controlled by your memory usage on your GPU. And then steps is just saying how many batches I need to feed through before I've exhausted my data set. A major thing to remember for all models, right, is you need to have the same preprocessing that it's trained on, right? So if you, for example, mean subtracted something from your data at training time, you need to do that at inference time as well. ResNet in particular was trained by subtracting off the mean pixel values, so that's what this guy does here. It takes each RGB pixel, subtracts off the mean of ImageNet from that pixel, and we'll do that when we pass it through the model. Keras uses something called generators to feed data into the model. It's exactly what it sounds like. It creates a Python generator, taking your input images, applying preprocessing to it, and then passing it through the model. This one takes a list of images. It's not available in the Keras library, but it's available in the repo that you could take a look at the end of the talk. And then to make predictions, you just call this predict on the generator for that number of steps. One thing I forgot to mention, just make sure when you use the generator, don't shuffle your data. You want the input to come in at the same order as you fed it in. Otherwise, the algorithm will be very confused. So again, we're going back to always visualize what you're doing. And so this takes those ResNet features and creates a nice little scatter plot of the images. One thing that's really nice about images and text is they're very easy to understand as human beings. We know what an image looks like, so we might as well look at the images in our data set just directly. And you can see here that these images kind of like picked up that variation we were worried about, right? We see the t-shirts are lumped together. They have a bunch of different variation in terms of color and size and all that, but they still are able to pick it up in the same part of the data set. Same as jewelry, same as shoes and watches. So in other words, these features, and we haven't even done any training of a model yet, are kind of very well separated, right? So we know that the model is going to work well, and we don't really have to worry about that kind of aspect. Okay, so that was a whirlwind of images, and now we're going to kind of go through the same thing for text. Text data is very similar, where we need to take text and then make it into some sort of numeric vector, right? So in this case, we're going to do the same example of our Swiss Army watch. In this case, what we do is we take the vocabulary in our data set, all the words in our data set, this make a long binary vector where we say, oh, is Swiss in the document? Yes, it is. We put a 1 in that vector. You know, is Army in there, and so on. So we make this very long sparse vector. This is kind of called like a bag of words type approach. So we could take that one step further, right? And so there's a bunch of different ways to deal with text. We're going to deal with something called TF-IDF and well as LSA and do the same kind of pipeline where we take that model, take those features and put it through a model. So what is TF-IDF? Just briefly, so there's two components to it. There's a turn frequency component, and the turn frequency component is it just counts the number of words in that particular document. For example, Swiss occurs once in the document, Army occurs once in the document, woman occurs once in the document, and so on. And so that's there. And then we have an IDF term, which accounts for the fact that a lot of words are not discriminative in terms of your model, right? So words like a, the, you, pronouns, and so on aren't very discriminative. And so we want to downweight those, right? And that's what this IDF weight does. So you can kind of think of it, N is the number of documents, like that's the number of samples. You might have 1,000 samples in your data set. And the document frequency is how many times it occurs in your full, the word occurs in your full data set. So if you have like a word like dog, it might occur 5 times in 10 documents. That would get a weight of 2. You might have another word like a, which occurs in every document. So that gets a rate of 1. And when you take a log of that, you get 0. So it gets 0 weight. So just again, scikit-learn library is a wonderful library for doing this vectorization. The TF-IDF vectorizer is right there. You instantiate the objects with a few nice parameters, n-grams, bigrams. And we limit the max words to about 5,000 because you don't need much more than that because you could look at kind of the word distribution and it's exponentially falling off. And then we fit transform and we have our TF-IDF weights. So back to visualizing, right? A nice visualization here is just a bar chart of the words. On the left, you have the words associated with the accessories label. On the right, you have the words associated with the clothing's label. And you could see kind of the common words. For accessory, we have stuff like watch, silver, sterling silver, stuff you kind of are expected to deal with jewelry. And then on clothing, we have stuff like shirt, different colors of shirts, large, so like sizes of the shirts, and so on and so forth. One thing I like about this visualization, though, is you could kind of see some problems with the way we did this, right? You could see things like quotes and ampersand, words that aren't very predictive that show up there. So you'd imagine going back and removing those from your data set and revectorizing. So just briefly, I really like those scatter plot images where you can kind of see how things are related to each other at a global level. And a way to deal with that with word vectors is this thing called LSA, latent semantic indexing. And what it does is it takes those TF-IDF weights that we had and makes kind of a space that has some global structure related to them. And just kind of a high level, what it does, it kind of decomposes this TF-IDF matrix into kind of concepts, right? So you might have a bunch of news articles. Some might be about sports. Some might be about politics, and so on. Those are your concepts in the news articles. And so there's these 3 matrices, a constants term. So that's going to tell you stuff like the sports concept might have like words like baseball, basketball, soccer, right? The concept matrix has things like the importances of the concepts of the document. So like, you know, are sports, you know, documents more common, for example, or not? And then the document concept is what we're actually interested in. And that's LSA. So that's going to tell you stuff like, oh, this document is mostly about watches, or this one's mostly about clothing or baby clothing, and so on and so forth. And so that's what we want. It's very easy to make these in using Python, using scikit-learn. We just take our TF-IDF vector originally and apply that decomposition, and that's that truncated SVD class. There's also this this function called make pipeline, which is very useful because it takes in you have a bunch of pre-processing steps. It takes all those, you kind of lump them together and get one class that you could use like anything else. So you could pass it through a pipeline, call fit transform on it, and you get these nice LSA vectors, right? Okay, so I made, again, another visualization of what we have here so we could kind of understand our data set like even better than we did before, right? And so you could see the color codings based on the class of the data, right? You have orange being clothing, and you have blue being accessory. And you could just see from here, even before we even look at what things are, that it's like very separable, right? We could kind of draw like a line between these two guys and see the different classes in our data set, which is important when you build your model because you can see it's going to be very easy to learn, right? So these are very good features. We can also see that it's learned something that's useful as far as kind of like clustering our documents. You can see hats are kind of up in the top left corner, jewelry is thrown down on the top right corner, and everything's kind of like related to each other. Kind of if you zoom in, you could also see like kind of like baby clothes and baby hats and stuff, for example, are all in the top, the upper part of the scatter plot. Okay, so now onto the actual modeling bit. Just kind of want to go over how you would do some basic modeling in Python for the features that we just came up with. So we're going to build a basic neural network model, and it's going to take what we did in the previous slides with the text. It's going to take the TF-IDF weights, it's going to take the ResNet model features, and it's going to combine those into kind of a very simple, shallow network that we can then get powerful predictions from, right? So the model looks like this. It's going to take fully connected kind of dense layers, apply them to those features, merge them together into like one single layer, so it takes those features and concatenates them together, and then we're going to put that through another linear layer to get your predictions outward. So again, we're going to use a library called Keras, right? And the basic Keras workflow is kind of like this. You kind of define your model beforehand like we did before, so you should always kind of write down your model like on paper what you actually want it to do before you even go into actually trying to fit it. Right, so you define it beforehand, you then compile it down, and after that you can't change it anymore. And then you could just fit that model using a certain optimization algorithm. So here's some code to do that. It uses the Keras 2.0 API, which is a relatively new API that I believe came out maybe a month ago. And again, so you just define it beforehand. The inputs are kind of what we said before. Those are the TF-IDF features, or the ResNet features. You have to just tell it, here they are, because you're not going to feed them directly through immediately. They have the shape of the number of the vocabulary size, right? And the ResNet features have the shape of the penultimate layer of ResNet. And then we kind of define the model we did before. Here's the right branch, right? It just, again, goes through a dense layer, and then through some dropout, which affects with overfitting. And then we have the images as well. Again, those go through two dense layers, same architecture, right? And then we combine them together using this concat layer. It just takes a list of the outputs, concatenates together in these one long vector, and then we put it through kind of a squashing function, right, to get our predictions outward. So that's kind of the define step, right, where we defined each component. And now we kind of do the fit step or the compile step. We kind of put it all together. We say our inputs were the images and the text, our outputs were the predictions, and then we compile it. In the compile stage, you kind of say, oh, this is what we want to optimize with. Atom's a good default optimizer. If you're just wondering what you should do, I would recommend that one. You have to tell it what to optimize, right? And in this case, it's binary cross entropy, which is the same thing as a log loss, which is a common loss for binary problems. And then we just monitor the accuracy metric. So yeah, so that's kind of how you define a Keras model, just the layers up front, and then you call compile. Fitting the model, again, we're going to use scikit-learn and a combination of that and Keras. So we use this label binarizer because Keras expects an input. So we have to take those accessories, which are text, convert them to kind of a binary matrix. In this case, we map accessories to 1s and 0, and clothing to 0 and 1. We use a class to do that because we might have to do this at test time or another time. So we need to save that to disk. And so we call fit and transform on our training and testing labels. We then define another generator, which takes in the TF-IDF features and the ResNet features and batches them out. So that just creates batches of size 32 that it then throws into the model. This is a function I have in the repo because it has to deal with sparse cases. And then finally, you fit your model, right? So you just call fit generator like we did predict generator previously. It takes your generator. It takes how many steps you want to run. In this case, that's going to be just our full data set. And then you optimize it. You can see here it has a nice little kind of display of the model as it runs. The accuracy already is doing very well. It starts out even at 90% accuracy right away and goes down from there, actually. So we knew that was going to happen just because of the visualization that we did before, right? That things were kind of linearly separable and looked very good. Okay, so finally, we fit this model. We saw how it did. We saw all the features. We have to be able to kind of, evaluate how well it did, right? And so the simplest way to do this is by just a single number. I wouldn't always recommend that, but it's a good starting point, right? And so this is a table of common metrics that you could use. The big takeaway here is you always have to compare it to some baseline. It doesn't mean anything. None of these numbers mean anything unless you know what you're comparing against. In this case, the baseline is just always predicting everything is clothes, right? We're just saying everything is clothing. And we can see we do much better than that, right? For accuracy, for example, it's 55% if you do closing, and we've made something that's 90% with not a lot of training time, right? This maybe took about 10 minutes to train or so on my laptop. Although that's not very insightful, because what we want to know now is how can we make this guy better, right? And this doesn't tell us anything like that. So we want to kind of dig further into what was different. And so here's an idea of a confusion matrix where on the left side you have clothing, accessories. That's what they're actually labeled. And then on the x-axis you have what the model thought they were, right? So the stuff on the diagonals, what we predicted properly, and then what's on the off diagonals, what we got wrong. So you can see here that clothing is getting predicted wrong a lot compared to accessory. But more importantly, just look at everything, right? Like we could just look at everything that was in the data set. A model, for example, thought this was clothing, but in fact it's just like a hat piece of jewelry, right? I thought it was clothing when I looked at it, but in fact it's a piece of jewelry because it's a hat besides that little keychain ring, and so that's why I thought it wrong. Same with this one, for example. It's a belt. We thought it was an accessory. In this case, it's clothing in the data set because it's kind of shiny, right? It looks like jewelry, right? So it's still, the stuff it's getting wrong is not too wrong. You could see why it's failing, right? And here's another example of something we thought was clothing, but in fact, the thing that was important here was the bag on this man's hip. And so it's just because there's a lot of stuff in that image, and it was looking at the wrong thing in the image. So finally, again, I go back to these scatter plots and just kind of, we plotted everything that we got wrong, right, into one global view. And we could see here really what's going on. And we could see the majority of what we're getting wrong is these bags. We're just very bad at classifying bags. And the reason for that is actually, I did some digging into the data set, and it's just because it's, they're kind of classified as both clothing and accessories depending on where they are, because it's the way the data set was made, where the labels came from where they would best sell. So bags sell sometimes good as clothing, or they sometimes sell good as accessories. And so here it's actually not really the model's fault, it's more of the data set's fault. And so this would be a case where we'd have to say, okay, we need to go back and kind of clean up our data set. So that was a very big whirlwind of how you would do images and text, kind of just give you an idea of kind of the basic pipeline in Python of how this would involve. There's things I didn't talk about, which is hyperparameter tuning. There was stuff like when we talked about those dense layers, that was at number 256, the number of hidden units. There was a bunch of parameters we just didn't even deal with. For ResNet, this is an idea called fine tuning, where you take that model and you kind of tune it along with the other the full model. Data augmentation is a very good one. So that deals with the fact when I was talking about all those things that could go wrong with images, size variation, and deformation and stuff like that. You could apply that to the images directly just to tell your model that, look, that's something you should look out for, and you should do that. And then, of course, trying different models. We just tried a very simple, shallow network. You know, you might want to try trees, or you might want to try linear model. You just might want to try other things that would work even better than what we did here. So yeah, so that's kind of like a brief whirlwind tour of images, text, data. And so again, you could find code for the stuff I didn't talk about in this GitHub repo, this PyData Amazon products. Check it out. How to make those plots, how to do all these graphs is up there. So yeah, and that's my email if you have any questions. So thank you very much. And if you have questions, let me know.
Thanks for the report.
Yeah.
So I have a question about text classification. You know, there is a common problem in this task is that sometimes text with a lot of errors in it. Mm-hmm. So the first problem is to make it more correct. So the question is it really worth effort to make text correct, or it's enough to train models on text as is, and if correct, so which tools should we use? Thanks.
Yeah, that's a very good question. So to answer that, I kind of have two different approaches to that. I think for one, it's worth just trying to see what happens when you just throw it in directly, right? Like it's a good baseline to have. Like it's probably not going to work out, but if it ends up working out, it's going to save you a lot of time later, right? That you would have had to deal with preprocessing and stuff like that, and you might only get a small gain. Now, a lot of times you do actually have to do the preprocessing of the text, and I'd recommend a few different libraries. My favorite library for text in Python is Spacey. It doesn't have support for every language, but it has support for like English, German, Spanish, so a lot of languages. So I'd recommend that for like actual like text preprocessing, stuff like looking at kind of name entity recognition, tagging, and so on. So it depends what cleaning you want to do, but that would be my recommendation as far as a library. Does that answer your question?
Hello?
Yeah.
Sorry, I'm here.
Ah, wonderful.
I have a little bit stupid question.
Sure.
The size of image, as I remember, it came from AlexNet, 224 x 224. Mm-hmm. So I see it being used in many model training.
Yeah.
But I never had time to figure out why. Why did you use it?
Yeah.
Like, what's the reason? Thank you.
So yeah, no, that's actually a really good question. So the reason for 224 by 224 is because in ImageNet, that's the size of a lot of the images, and the model we used was ResNet, right? So once you define the model, we're taking a model that someone's already made, and they define beforehand what the input image size needs to be. And once it's been defined, you can't change it. And so we need to just conform to what they've already given us, right? And they say the input's 224, and we need to conform to that. So you just have to make it 224 by 224. The size for that, the reason for that is kind of a memory issue. If you have too big of images, it's going to kind of, your GPU is going to run out of memory. So we can't just make them as big as we want. And the reason they can't be varying sizes is, again, it's just these static architectures, right, where we had to define it beforehand. And when you define it beforehand, that means setting the shape beforehand. So you can't just have a dynamic shape changing. And so yeah, that's where it came from. Yeah, partly a GPU limitation and partly a limitation of these static definitions of models where you can't change them after the fact. Yep.
I have a question. Mm-hmm. So when you choose the model, you had this elbow-shaped plot of different models and how you choose them.
Yeah.
Does the fact that you need to only classify into classes help you to choose one?
Yeah, that's a good question. So in this case, I think the bigger question, right, is how close your data set is to ImageNet, right? Like in our case, this data set had classes that were available in the pre-trained images. And so we could get away with choosing a less accurate model because, for example, like it would be, these guys are similar, so we didn't have to worry too much. If we were doing stuff maybe like like cancer classification or something very different, we might want to choose a bigger capacity model because we'd have to kind of tune that more. It would have to kind of learn more abstract features. Now, the model we chose, the reason we chose it was because if you looked at kind of that elbow plot, we kind of got past ResNet 50 and it kind of leveled off, right? And since it leveled off, as you go, okay, so as you go across, the images got bigger or the dots got bigger. And truthfully, once you get too much bigger than that, you can't fit anything on the GPU without doing kind of like multiple, or getting a big GPU. And so the reason I chose that was inference time and GPU capacity. So it didn't really have anything to do with binary images, but more my compute power at the time.
And then I have another question, if time allows. So returning to the business task, now we need to classify for the shop. Now, does it say anything about what to do with false positives and false negatives? Because operationally, this seems to be the most hard thing in all of these businesses.
So the question would be kind of like how important, so if you're more worried about a false positive, right, you might want to build a model that has a low false positive rate, right? And so that would be something when we talked about kind of this confusion matrix up here that you maybe wouldn't want to look at accuracy as your metric. You might want to look at this precision, this true positive accuracy metric or another metric. And so it kind of depends on when you're ranking your models, when you're trying what model, what you're going to focus on, right? If that answers.
Thanks.
More questions?
All image classification programs that I saw manipulate the raster images. Do you know of any efforts of analyzing the vectorized or some other forms of imaging?
Yeah, like an SVG image or something like that? Yeah. Usually you just have to convert it to something like a JPEG or a PNG and stuff like that at the end of the day. I mean, at the end of the day, they all manipulate arrays, right? So as long as you can convert it to an array of numbers, that's all that matters at the end of the day. Because they all have to have a fixed size. It doesn't matter if it's a vector length, like a vector image, because it still needs to be fixed size when you feed it into the algorithm. So that's not really a satisfactory answer, but I don't know of any. All the ones I know work on kind of static images.
Questions?
Hello. I've got two questions. One of them is about the library you've used for image analysis. Why did you use Keras? Did you try it, Tiana and Lazarne? And another one is how do you have any incremental way to compute TF, IDF? I mean, for every word you have to number words. So, I mean, then a new word comes. How do you just recalculate all the model for all the text you have, or you have something that helps you?
Yeah.
Oh, that's if you understand the question. So
that's a very good question. So the first one was, why did I choose Keras as opposed to another library? And the reason I chose Keras was because it's probably the simplest one to get started, right? If you just kind of have a simple architecture in mind and you don't want to, so like the other libraries, for example, like Theano, TensorFlow, it's kind of like dealing with NumPy as opposed to dealing with scikit-learn, right? It's a low-level library as opposed to Keras, which is a high-level library. So I chose that because, again, it let me not have to deal with the low-level details and just deal with the abstractions. So when you're doing something like this where you're trying out a bunch of different models, the ability to iterate quickly is important, right? And that's kind of something that Keras gives you, is ability to try different stuff quickly. And then if you're worried about optimization, maybe for deployment or something like that, then you could switch over to something low level where you could really tune things to your specific needs. Your second question was about TF-IDF and what happens on very large data, right? Like if I can't fit everything into memory. And so you're right. So for TF-IDF, you could calculate things in batches, right? So it does require a full pass of the data. You can't get around it where you have to go over the full data and then look at your vocabulary size. Now, for very large vocabularies, that could run out of memory very fast. And that's one thing why I set the maximum vocabulary size. So we only use a vocabulary of about 5,000 words. So basically what you can do is you could basically set up a way you go over and you drop words that aren't occurring very frequently or occurring too frequently to keep the vocabulary size static. And there's a library called Gensim. The scikit-learn library doesn't do it, but there's a library called Gensim that will do it in an online fashion if you're worried about memory constraints. Now, as far as the size, it keeps it in a sparse matrix, right? So that's very different than a dense matrix. It only keeps the non-zero values. So this could actually scale relatively well as far as memory size, kind of answer that other question. So it's expensive, but it's actually relatively fast. Compared to some of the other things we talked about in here, like the model fitting of the network, the calculation of TF-IDF is usually relatively fast, because it only takes about one pass over your data set usually to get the result. Does that answer your question? Good.
Okay. Thank you.
Thanks.